Today, we're tackling a classic, Tic Tac Toe. Given a sequence of moves, can you determine the winner, if any? Or is it a draw? Or is the game still pending?
This isn't just about simulating the game, it's about efficiently detecting a win condition. The problem provides a list of moves, where each move is a coordinate pair. Player A makes the first move, then player B, alternating. We need to return A if player A wins, B if player B wins, draw if the board is full and no one wins, and pending if the game isn't over yet. The board is always 3 by 3. A straightforward approach is to simulate the game by building a 3 by 3 board.
After each move, we'd iterate through all rows, columns, and both diagonals to check for a win. If a player has 3 of their marks in a line, they win.
If all 9 cells are filled and no winner, it's a draw.
Otherwise, it's pending. This approach works, but repeatedly scanning the entire board after every move is redundant.
It's big O of n time where n is the number of moves, but each check is technically constant for a 3 by 3 board.
Space is big O of 1, constant time for the board. The key insight for optimization is to track the state of each row, column, and diagonal incrementally. Instead of a full board, we'll use a few integer arrays. We'll have an array for rows, an array for columns, and 2 variables for the diagonals. For player A, we add 1 to the relevant counts, for player B, we subtract 1. A win occurs when any count reaches 3 or negative 3. For example, if rows at index 0 becomes 3, player A wins that row. If it becomes negative 3, player B wins. We check this after every move. This avoids full board scans.
If no winner is found after all moves, we check if the total number of moves equals 9 for a draw, otherwise it's pending.
Let's trace an example. Moves 0 0, 2 0, 1 1, 2 1, 2 2. Initializing row counts, column counts, and diagonal sums to 0. First move, 0 0 by player A.
Add 1 to rows at 0, columns at 0, and the main diagonal. Next, 2 0 by player B, subtract 1 from rows at 2 and columns at 0. Then, 1 1 by player A. Add 1 to rows at 1, columns at 1, and both diagonals.
No win yet.
Next, 2 1 by player B, subtract 1 from rows at 2 and columns at 1.
Finally, 2 2 by player A. Add 1 to rows at 2, columns at 2, and the main diagonal. At this point, the main diagonal sum reaches 3. This means player A wins. The final result for this example is a
player A successfully completed the main diagonal, triggering the win condition when its sum reached 3.
The game concluded before all moves were made.
You'll spot this pattern when you need to check for line-based win conditions in grid games, especially when the grid size is small and fixed. Anytime you're repeatedly calculating sums or states over rows, columns, or diagonals, think about incremental updates using prefix sum like arrays. This optimal solution has a time complexity of O, m, where m is the number of moves, as we process each move once. The space complexity is big O of 1, constant time since the board size is fixed at 3 by 3. This incremental tracking strategy is powerful for many grid-based problems.
Try the next problem to reinforce this pattern. Don't forget to like and subscribe for more efficient algorithm breakdowns.